We are proving this thing, no? So in this case, which we have just proved now, the first exponent was positive and the second exponent was negative. But here the first exponent is negative, second exponent is positive. We can switch their positions. So now this becomes the first exponent, which is positive, and this becomes the second exponent, which is negative. So by this case, the previous case, we have where am I writing? A to the power n dot a to the power m we are getting now. Am I writing it correctly? Yes. Okay, there is no problem with this calculation. The only problem is that it will not work. I want a to the power m dot a to the power n. Oh, instead of using the previous case like this, what I can do is this. Okay. The case m less than 0 and 0 less than n follows from the case n less than 0 and m and symmetry. What does it really mean? You see, whatever we have done here, we have proved this result when n is less than 0, 0 is less than m. We can also prove switching m and n. These are just names given to some integers. So from the symmetry of the situation, if you do the same thing with m in place of n and n in place of m, then you will get this. I mean, what I am trying to say is that whatever you have done here, an exact similar thing can be done in this case. So instead of it, if we go through this case again like this, it will be some sort of a repetition. So when we come across some situation like this, we don't usually do it. We leave it by writing something like this, and that covers all the cases. So hence or I can write like this. This proves the first identity. Okay. Next, we prove the second identity. Okay, here also we are going to use induction, but induction on what? We are going to use induction on n. The second identity is, of course, this one. But before we go for that induction proof, let us note that the identity, just like that one, the previous one, is trivially true if n is 0 or n is 0. Let us see what happens when we have m equal to 0? If we have m equal to 0, then on the left hand side we have e to the power n. Here however we have a to the power 0 itself, so we have e. So it seems to suggest that e to the power n is equal to e for any integer n. Now this thing seems like it's a trivial thing, but this also needs a proof actually, and you can prove it by induction on n. Okay, keep in mind that only you can apply induction only in the case where n is a positive integer or a non-negative integer. The negative case you have to again separately settle. That can be done, and this is left. So although this looks like some work needs to be done, but still it is left. It is trivially true. What happens when n is equal to 0? That case is even easier than this one. If n is equal to 0, you have this. So on both sides you have identity. So that is true. So assume m and n are both non-zero. Okay. We now prove the identity for all integers m and all positive integers n by, some ink is needed. By induction on n, keeping m fixed. Note that unlike the previous identity, here we are keeping m fixed, but at the same time m is any integer. M can be negative also, or m can be positive also. N by induction on n, keeping m fixed. When n is equal to 1, we have, okay, what happens when n is equal to 1? Here a to the power m whole to the power n is equal to this, which we already know. Anything to the power 1 is that thing itself in a group, and this can be written as m times 1. So in this case the result is true. So the identity holds when n is equal to 1. This is the basis for our induction. Now we are going to assume that it is true for some positive integer n and true for n plus 1. Assume this for some positive integer n. Okay, now what happens when we take n plus 1 in place of n? Then all we can do here is apply the definition. So this will be equal to be careful, a to the power m times a to the power m whole to the power n, the element times the element with that exponent. Here we apply the induction hypothesis, so this becomes a to the power mn, and here now we can apply the first identity and write this as m plus mn. Note that ideally we should write all these things. All the steps, the justifications for all the steps should be written alongside or somewhere, but I am not writing it since I am narrating the thing, the whole thing, or rather describing the whole thing, so I am not bothering to write those things. It follows from the first identity. You can sort of see that it follows from the first identity, and this becomes a to the power m times n plus 1. So this completes the induction. Okay, since we have gone through several inductions, this completes the current induction, the latest one. Now we are left with the only case where n is negative. Okay, so what happens in that case? So I believe just like the first identity, this also needs something. Okay, again a statement for you to prove. It can be proved that for any integer k, any integer k, or we can write any positive integer k, or have I written, okay, k, any integer k, a to the power k inverse is equal to a to the power minus k, which is equal to a inverse to the power k. This also you can prove just like that other one. Okay, I am not commenting anything more on this. And now we are going to use this and settle the case, last case where n is negative. Now, if n is a negative integer, then a to the power m whole to the power n, by definition, this is the definition, it's available to us. So this is the inverse of a to the power m to the power minus n. See, here in place of a we have a to the power n, so that's how we have like this. Okay, now this is where we use this part. A to the power k inverse is equal to a to the power minus k, or we can use this one also. Which one have we used? We have used this is equal to this, with a to the power m in place of a. No, sorry, a in place of a, because we already have k. So anyway, this is according to that thing. is going to be equal to A inverse to the power m to the power minus n. Okay. Okay, now you look at this. This looks like something like this. B to the power m whole to the power minus n. Keep in mind what we have already achieved here. Above this, we have proved the second identity for arbitrary integer m and non-negative integer n or positive integer n, because the case 0 is trivial. So for positive integer n, so now since n is a negative integer, minus n is positive. So by what we have proved, we can write m times minus n. This is justified by this part of the proof. Now in place of b, we have A inverse. So this will be equal to A inverse to the power m times minus n. I hope you can see this. M times minus n, and this becomes A inverse to the power minus mn. Okay. Now after this, how did I write A to the power mn directly? Directly I cannot write A to the power mn because m can be negative also. Okay, now cases will appear. So what I have done here is wrong. At the last step I have committed a mistake. If m is negative, then minus mn is positive, and we are here. If or in other words, if m is negative, then we have A inverse to the power a positive integer. So from this part of the definition, you have A to the power m whole to the power n equal to is equal to this. Do you understand how this second part of the definition has been used here? In place of minus n, we have minus mn. Minus n is a positive integer here, minus mn is also a positive integer. In its place, we can write A to the power n, that is, we change the sign of minus n. Here in place of minus n, we have minus mn, we change its sign, so that becomes plus mn. M cannot be 0, we have already gotten rid of that case. What happens now if m is positive? Okay, if m is positive, then this means that in my system, the solution that I have typed out, that also has a mistake here. I have to rectify there anyway. So if m is positive, then minus mn is negative, because minus mn is negative or positive. Okay, I am getting confused here. N is already negative. Okay, so if n is negative, then minus n is positive. Oh, sorry, I forgot about n entirely. Thinking about m, I forgot about n. If m is positive, since n is negative, So minus n is positive, m is positive, so that means here I have positive. Okay, now in this case I have positive, and in this case I have negative. Okay, then sorry about that confusion. If m is less than 0, then this is equal to this, we have already proved. Okay. Now what is the final sign of minus mn? It is negative, because minus m is positive but n is negative. So that means according to our definition, this is A inverse to the power mn. Do you see why? In place of n, now we have minus mn, which is negative. So we would have to put the base with an inverse. I mean, we have to put minus 1 on top of the base. Now our base itself is A inverse. So we have put A inverse to the power negative of the exponent. Our exponent is minus mn, negative of that is mn. Now A inverse according to our that previous elementary result, I think lemma 231 or something like that, is equal to A. So A to the power mn. So this completes the thing in its entirety. We can write hence the second identity has also been established. Now we resume our exercises. We have the laws of exponents or the rules of exponents proved for us. We can now freely use them. Okay, so now we go to exercise 2. So what does exercise 2 say? Prove that if G is an abelian group. It's not very difficult, quite easy. If G is an abelian group, then for all A and B, for all elements A and B in G, and all integers N, we have this. Again, this is also a law of exponent which you see in the context of real numbers and their powers, but that is because multiplication of real numbers is commutative. That's why you see we need G to be an abelian group. Then A dot B whole to the power n is equal to A to the power n dot B to the power n. We have the habit of taking this type of calculation for granted in the context of ordinary numbers. That's because all the operations are commutative. Here also, just like the previous one, or we can start our induction from n equal to 0 itself. Oh, I could have written it just like that, or let let us just mention, we apply induction on n to prove the result for all integers n greater than or equal to 0. The result is trivially true for n equal to 0. It's especially easy to see why it is true. Assume for some integer, for some non-negative integer, then to the power n plus 1. Then by the definition of, we don't have it anymore, you can either use one of the laws of exponent, or you can use the definition of integral power to write it like this. Let us use the law of exponent, that will be better. This, the first law of exponent. So according to our induction hypothesis, this is equal to a to the power n dot b to the power n, and this comes from the definition, and it is equal to a dot b. But now we use the fact that it is given G is an abelian group, so the operation is commutative. We can change the order of a product however we like. So in place of a dot b, we can write b dot a. One application of the associative law gives us this. Another application gives us this. Okay. Now in place of b, you can write b to the power 1 and then use the first law of exponent. Doing that, you will get this. Again use commutativity to write b to the power n plus 1 dot a like this. Then again use the associative law. And then the road ahead is clear. Although I said we should not skip steps, but in some pretty obvious cases where you are absolutely sure that whatever you are doing is correct, you can skip steps. You see, we have written here, directly we have written b to the power n plus 1, but we should have written one more step where in place of b, we would write b to the power 1. But since that is trivial, so we are writing like this. What have I, okay, see, without noticing we make such mistakes. This is not, I had n plus 1 in my mind, so inadvertently I wrote n plus 1 here itself, so that's a mistake. Now I have n plus 1. Okay, so this proves the result for all non-negative integers n. Now we go to the negative part. If n is a negative integer, then a dot b to the power n by definition is a dot b inverse whole to the power n. Now here again we are going to use one of the things that we have come across in lemma 231. There part D says that the inverse of the product of two group elements is the product of their inverses but taken in opposite order. Oh, here I should have written minus n. Okay, so that is this we are getting from lemma 231 part D, but our group is given to be abelian, so it can be written like this. And now we have a product of two elements again. After all, A inverse and B inverse are also group elements, and the thing we have proved when n is non-negative, here A and B are any group elements. Okay, so actually when we write assume this for some integer n greater than or equal to 0, we should technically speaking write this for some integer n greater than or equal to 0 and all A and B belonging to G. Okay, so the induction, although it's happening on n, but A and B can be any group element. We usually don't write this part because that is understood, but keep in mind that in the background that is there. So that's how now I'm going to now I'm able to use that here, because minus n is positive and these are two group elements. So I can write A inverse to the power minus n then again by our definition this becomes equal to A to the power n dot B to the power n. So that completes the solution to the second exercise. Okay, so then what is the third one? It's a characteristic of Herstein's exercises that first he will start with some pretty basic, almost trivial exercises, then all of a sudden an extremely complicated exercise will be presented related to the previous ones. So exercise 4 is one such thing, but let us first see exercise 3. If G is a group such that A dot B whole square is equal to A square dot B square for all A and B belonging to G, then show that G must be abelian. You see that this is in a sense a sort of converse to this one. If the group is abelian, then this is true for all integers n. However, if it is true only for n equal to 2, then the group must be abelian. Here the solution is quite straightforward. Note that A dot B dot A dot B, look at this product. If we use associative law first inside, we get this. Then we use associative law outside, we get this. And we have already seen that the product of an element with itself in a group is its square. And that, according to our condition, given condition, is a square dot b square. Now a square can be written as a dot a and b square can be written as b dot b, and this will be equal to again we apply associative law. A dot b dot b, we apply it once and then inside we apply it once more. Now what we do, now we use the cancellation laws that we have come across in lemma 232 in the second lemma of the third section by or by the left and right cancellation laws. Of course, we won't refer to these results by lemma by saying lemma 232. This is in general, that's how we say it, by the cancellation laws, or by the first you apply the left cancellation